Hello, hello, hello. Welcome, guys. I'm glad you're back. We are getting ready to talk about electron configuration. So this is our fourth fourth lecture, third real lecture that we're talking about stuff. So I decided this term to pull electron configurations into its own lecture. This is a difference from what I've been doing in the past because I used to do this with the next lecture, which is names and formulas. And that lecture ended up being really, really long. And I thought that, and it ended up being very, very complicated for students to understand. So I figured it would be better to pull it into two lectures. Now, then it's questionable whether they're long enough. I think that's probably okay. I think again with both of these are things that we need to be doing a lot of practice on because with both topics, it's really important that we get how they work, that they are very, very important to how we do the rest of the course. So I think it's better to have more practice with these things and spend more time on them than to power through lecture and be done with it. So that is the plan with this. Now, what you'll notice because of this is that we're going to skip a quiz for this. So right now, there is no quiz that goes with this one. I was going to go in and make another one and renumber them all and yada, yada, yada. And I don't think I'm going to do that. I think for this term, I'm just going to move them all to the next lecture. And so you may see some electron configuration stuff on quiz 4, which goes with that lecture. And I think I'm just going to leave this one with no quiz for it. So hopefully that will avoid the issues of it doesn't really match the way that it's supposed to go, because this is where I made the biggest change to where things are. So hopefully that will take care of it. I think that was it. I think that was the only thing I had to talk about. So let's go ahead and talk about electron configurations and let's see what we've got for this. I have an extra space. I'm sorry. So we're going to be talking about some things going with electrons, protons, and neutrons. We talked about that last time, so it's going to be a review of those things. We'll talk about quantum numbers. We'll talk about orbitals, both of which are new ideas that we haven't really talked about. And then we'll talk about electron configurations. Now, understand that quantum numbers and orbitals, both of these things are going to be stuff that we talk about information only. So you won't need to know any of that. It's just to help you understand, and it may or may not help, okay? But it's not stuff you'll get tested on, right? Okay, now, a review from last time. I want you to draw me an atom of 13,9 F minus, showing me the number of electrons, neutrons, and protons. Awesome. This is based on what we did in the last lecture. So I want you to pause. I want you to take some time to do this. This is one of the quizzes where, and this is based on the quiz that you're doing for this lecture. This is one of the quizzes where you should be turning in this work. There is a quiz scratch in the assignments, so you would turn that in there so I can take a look at it. Again, these are pass-fail, but if you turn in something that looks really weird, that way I can talk to you about what that's supposed to look like. So take a pause and see what you can do with this. Okay. 13,9 F minus. Now remember, when we talk about 13,9 F minus, 9 is the atomic number, so 9 should match F, and so F's atomic number should be 9, which it is. So 9 is the number of protons. 13 is the mass number, which is equal to the protons plus the neutrons. So if I want to solve for the number of neutrons, I take 13 minus 9, and that gives me 4, and that's equal to the number of neutrons. Okay, so that's the number of neutrons I have in this particular species. And the other thing that I know from this is that F is a negative charge. That means it has an additional electron compared to what it normally has. Now, in its neutral state, it should have the same number of electrons that it has protons. So it would have 9 electrons. We're adding 1 electron because of the charge. That means it has 10 electrons in this configuration. So that's the number of each of these things that I need to distribute in the picture that I'm about to draw. And remember that we're going to have our protons, neutrons, and our electrons. Those are the things that I'm going to be drawing. I'm going to have my protons and my neutrons in the middle part, my nucleus, and then my electrons are going to circle that. Since it's a Bohr model of the atom, we're just going to have them encircled around it. Okay, it doesn't really matter. At this point, you have no reason to draw them in any way, shape, or form other than a circle. Okay, you don't know anything else about it. So right now, I'm going to draw 9 P's like this. Notice I have not put any charge on this, and that's okay because I said that's what a P was. So as long as I label that, when we're drawing a Bohr model of the atom, it doesn't need to be accurate in terms of our charge. You'll see this. So some of the pictures that we have don't include that charge there. So that's okay. So there's 4 there. I've got 5, 6, 7, 8, and 9. So that's my protons. I know that I need 4 neutrons. And there. And put it in over here. Here. And put it in then right here. So 1, 2, 3, 4 neutrons. That's everything that's in my nucleus. I got a little weird thing over here, but that's all in the center. And then I need to have 10 electrons. So since I don't know anything about where they're supposed to go, I just know they're supposed to go on the outside. I'm going to draw this circle right here. I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 10 electrons outside. That is a perfectly acceptable picture of a Bohr atom based on what you know right now. Okay, so that would be acceptable for this. Now, were there other ways you could draw this? Absolutely. All right. Could I do it with other things? Yes, I could. Right. I would accept other answers. I would accept, 3 circles instead of the 1 circle. I would accept 2 circles instead of the 1 circle. And of course, we might have 2 circles because I know that F is in the second row. So you might say, well, it needs to have 2 circles because there are 2 energy levels there. You might know that, so you might draw 2. I might have people that draw 3 circles because they know that there's row 1 has an S type, or 2 has an S type and P type, and we'll talk about those today. So we might end up with 3 of them. It's okay. Right now, you don't need to know that. So it's okay, no matter how you decide to draw this at this point. This is based on the knowledge you have at the moment. Right? So questions, comments, problems on that? Hopefully not, but if you have them, go ahead, tell me what we're talking about. You have questions about the quiz, and we'll talk it through. Okay? All right. So that's a review from last time. Now, like I said, the quantum number information is to help you understand what you're looking at. We don't necessarily ask a lot of questions about the quantum numbers. We consider this information that you don't really need in the long run. Remember, we're trying to focus on the things that you'll remember in 5 years. This is not information that you necessarily need in the long run, so we don't necessarily talk about this in that detail. But some people find it very, very useful to talk about this. And I know for me, I didn't understand any of this without talking about the quantum. And that's why I present them. Okay. Quantum numbers represent 4 numbers that are associated with any given electron. There are 4 quantum number types. There's an N, an L, an ML, and an MS. N is my principal quantum number. It's the energy of a given orbital. Okay? An orbital is a place where electrons live. It represents a statistical distribution of where an electron can be found. Right? Is it a real structure? Not exactly. It's based on statistics. That's where we typically find that electron. Those electrons are free to move, and so they move in other ways too, but it's the statistical distribution of where we would find it. Possible values for n are whole numbers going between 1 and 7. Now, why do I know they're 1 and 7? That's an interesting question. And I'm going to tell you that it's based on something that you might be familiar with. Remember we talked about our periodic table, and I pulled up this one from the RSC. What we're looking at is that there's 1, 2, 3, 4, 5, 6, 7 rows. So there are 7 periods that are available. The lanthanides and the actinides, if you remember, actually go in here. So the lanthanides fit here, the actinides fit here. So there are 7 energy levels that we are aware of. We haven't really seen any evidence that there's anything above that. So that's what we're aware of, and that's what that N represents. It's that energy level. Okay, so you can think of it as being the same as a rho number. All right. So that's the kind of thing we're talking about with our N's. Okay. So N I tend to think of as a rho number. When we talk about an L is described as an angular momentum. And it's the shape of an orbital. Now, there are different types of orbital shapes. All right. When we talk about orbital shapes, I'm going to flip over for just a second to look at the next slide. When we talk about orbital shapes, oh, it's not that one, hold on. It's over here. I'll go back, I promise. When we talk about orbital shapes, we have some shapes that are roughly spherical, so the electrons spend the most amount of time in a circle at a certain distance from the nucleus. Some electrons spend more time in what looks like a dumbbell shape, so more like this. Okay, and it is 3-dimensional, so it's not just in one dimension that we do this. Some electrons spend more time in a 4-leaf clover type shape, and of course there is a mathematical combination of them that looks like this. So we have a dumbbell with a circle around it. That's another mathematical combination of them. Okay. Now there are F shapes, and I showed you those the last time. I will never ask you to draw them, but there are statistical distributions for each of these. So the S-type, the P-type, the D-type, and the F-type look different. Remember when we talked about the S-type, P-type, D-type, F-type last time, because I did mention this, we said that there were places on the table that we could find these. And we have our S block. This is where we find those spherical ones. That's what the S is for. We have our P ones because they look sort of like a P. I'm not really sure why. I think it has to do with pi. I think that's why they're called that. We have our D's because we've got the thing, whatever. It's S, P, D, and then F. That's where we are. So if you wanted to, sometimes we label our periodic table to say S block, P block, D block, and F block. And notice I'm doing it in what most people think is a weird order, because I go S, and notice this one's an S2, and then P, which is over here. And people are like, well, why did you skip this one? And then D, right? So why did I go S, then P, then D? It's because that's the order that the numbers go. Okay, so that's why we talk about them in that order, because it's the order the numbers go, and that implies that's the order that they fill in. So that's why we would do that. And we'll talk more about that as we do electron configurations today. Okay, so those are our blocks. Now we're going to come back, because that's what I mean by the shape of the orbital. So again, those could be S, P, D, F. There are G's and H's as well. The G's and the H's are a statistical distribution that we see when an electron is in an excited energy state. The excited energy states typically have to do with I've hit it with some kind of energy and it now has more energy than it used to. And so, it can do things like fluoresce or luminesce. So it can give off energy from that state. And that happens when it goes from one of these G's or H's back to where it should be. I'm not going to worry about that part of it, but there are these places that they can go to when they get excited. Those do exist. We only are going to be worried about the S, P, D, and F, so the ones that naturally occur on the table. Right? So those are my shapes. The next one that I talk about, and the values for those can be whole numbers up to n-1. So if I'm in row 1, I can only have one S or one L number, which is 0. And 0 corresponds to an S. So in row 1, I only have an S type. Notice that. We only talked about an S type. So row only has an S type, because remember, that's an S. So this guy over here is an S. So row 1 only has an S type. I'm going to pull this over here so we can talk about them together. Okay. And when we talk about n-1, if we go 1, 2, 3, 4, 5, so we're now in period 5. If I talk about period 5, that's this guy right here, okay? And this guy right here would then have possible n values of 4. So if he has possible n values of 4, so up to n-4, he can have S, P, D, F, and G, right? So those are things that we, oh no, wait, that's actually 4. 1, 2, 3, 4, 1, 2. Yeah, okay. Hold on, let's talk about this one instead. No, I don't want to click on that. I want to do that. So let's talk about 4. This is actually, this is 4. Is that not what I clicked on? Okay, never mind. So this is 4. If this is row 4, then it can only have values of 3. So my orbital shape can only be up to 3. So I can have an S, a P, a D, and an F. Okay. So I've got the S block, I've got the P block, I've got the D block, and I have an F block, but there's nothing in it. Okay. So the fact that there is one, but there's nothing in it, means that we can do some things with it. All right, and we'll talk about that eventually. We will talk about it, but that is what we're talking about. Okay, so we have those things available to us. So that will determine where we can put our electrons, is where these things exist. So in row 2, when we're talking about row 2 right here, the only values of n that I can have, if my row number is 2, my L values can only be 0 and 1. So I have an S type, which is a value of 0, and a P type, which is a value of 1. So you can see that I have an S type here and a P type here. Okay? And that's what I mean. It helped me to understand that those are all I can have because of these quantum numbers. All right? Because I was like, well, why can't I have all these other things in these other places? Well, I can't because those are the rules. Now we go to the ML. Now, ML is described as the magnetic quantum number. It's the direction of the orbital in space. So it has to do with, is this pointing up? Is this pointing down? Now, a spherical thing, that makes no sense, right? Because a sphere doesn't point anywhere, right? So my sphere is always like this. So its magnetic quantum number is always 0. And that has to do with it can only be these values. We'll talk about that in just a second. But when we're talking about the direction in space, when we talk about our p's, that makes sense. It's either an x, a y, or a z. And so we can talk about which one of those it is when we talk about where that electron is. It's either in the x, the y, or the z. Okay, it doesn't move between them. When we talk about the d orbitals, there are descriptions for each of those. I'm not going to go through what they are, but each one has a designation, and that any given electron is in one of these, not all of them. Okay. Think of this like an apartment. So what we're talking about is, where does that electron live? We're giving it a specific address. So when we talk about this, we're talking about, okay, what city does he live in? What street does he live on? What is the street address that he lives on? And then the next one that we're going to talk about would be his apartment number. That kind of thing. Right? So this is his direction in space, which means the specific orbital. So which one of them is it in? And it says that I can have values of negative L to L, including 0. So if I'm in row 2, so row number 2, which is the one that I have highlighted, then my L values can only be 0 and 1. So I had S and a P. My ML values can only be negative L to L. So if it's 0 and 1, give me negative 1, 0, and 1. And that corresponds to the X, the Y, and the Z. That's what I mean. So we have correspondence to the 3 orbitals that are there. Okay? That, in my opinion, was the easiest one to see. Okay. There are 2 L plus 1 possibilities available. So if, again, my L maximum value is 1, 2 times 1 plus 1 is 3. And that's exactly what I see is 3. Okay. So that's that. So now we can look at this last one. It's my MS. We call it the spin quantum, and it indicates the direction of the spin. Now, every electron has a spin to it. Right? What that means is that it does spin, all electrons spin. What we typically, how we typically represent that is it's either a spin up or a spin down. You may have seen people drawing them this way. Okay. Why we do it up and down and left and right, I'm not sure, but I think it's just it is a convention that we use. That's what we do. The spin quantum number indicates the direction of the spin. So, it indicates which one of the 2 it can be. Right? For reasons that we'll get to, any particular orbital can only have 2 occupants. And this tells me which one it is. Of the 2, which one? It's either the up or the down. Okay? So it's negative 1/2 or 1/2. And we give them half values because they're spins. One of the things that you're aware of is that some things are magnetic and some things are not. What happens is that if I only have one electron in a particular orbital, it's not paired with another one, that's when I have a net spin. And so that net spin is then attracted to that magnet. Okay. If I have paired spins in all of my orbitals, then there's nothing that I can attract because they effectively cancel each other out. So the positive 1/2, the negative 1/2, those 2 things cancel it. And so we don't see magnetism in those species. Okay. And I want you to think about this from a practical standpoint, right? If we really think about this, and instead of talking about this as the apartment that it's in, if we instead back up and we say, okay, this is the room that they're in, this is the apartment, this is the street address, and this is the street. If we're talking about who's in that room, right, I need to know which of those people it is. And in that room, we can only have two people, right? And when we talk about this, for reasons that, I mean, we can look at this as it's a heterosexual couple. So it's either the male or the female. It's either the up or the down, right? What we can't see here, by our analogy, we can't have two up and we can't have two down. It cannot happen. It's just not possible in this little scenario that we're looking at. So that makes it a bad analogy, and I understand that, but that can't happen. Okay. So that's what we're talking about. We're trying to find out exactly which electron we're talking about by talking about where it lives. So what's its energy level? Okay. What shape of the world does it live in? Which direction orbital space does it live in? And which spin does it have? Right? And of course, these are the possible quantum numbers that it has, which again helps me to understand why we can only have certain types of orbitals. So there we go. Okay. Now, this is just a table of possible quantum numbers for these things. And when we start talking about where these things live, when we start talking about where the electrons can live, one of the things that you may have noticed already is that we only have an S in the first row. In the second row, we have an S and a P. In the third row, we have an S and a P. That's what it looks like. But we should be able to have an S, a P, and a D, right? We should be able to see that. And that's interesting to us. Okay, so this third row should have an S, a P, and a D, but right here, there's nothing in it. So the question becomes, well, okay, if it has it, why doesn't it fill it? And we'll talk about why. But, understanding that it has that thing, it is there, but we're not filling it, became very confusing to me. So this helped me to understand that I have an S, I have an S, a P, I have an S, a P, and a D, and those are the ways that we do that. All right. Okay. So I showed you our orbital shapes. Now, one of the things that I said when we were talking about spin up and spin down was that any particular orbital can only have two electrons in it, and that is absolutely true. So if it only takes two electrons, then an S-type orbital, because it only has one orientation, can hold two electrons. S has two. P, because there are three of them, each one holds two, and therefore the S block can hold six. Remember that. So P can hold two, one, two. Or sorry, S can hold two, one, two. P can hold six, one, two, three, four, five, six. D, there's one, two, three, four, five, each having two electrons. That should be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 of them. Okay. And F, so if this is 5, then I know the next one there are 7 of them. Okay, for reasons that we've talked about, I know that that's the number of them that exists. If there are 7 of them, each one containing 2, then we should have 14 total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I don't have to remember how many of them there are. If I know that each can hold 2 and I can count that there are 14, then there must be 7 f orbitals. Okay, so I should be able to use my periodic table to understand how many of these things there can be, right? For me, learning to associate things with my periodic table makes my life a lot easier because that table is available to me on a test. Now, I can't label that table before I go into a test, but I can learn in my head to associate this with the S, the P, the D, and the F. And then as soon as I get into the test, write S, P, D, and F. Now, I told you I'd tell you why I did it S, P, D, F, right? And that's because as we go through this, row 1 has an S right there. Sorry, right here. Row 2 has an S and a P. Row 3 has an S and a P and a D. And that's why. Okay. So as we continue to go down, we have S, S and P, SP and D, and then we get S, P, D, and F as we go down. Okay, so that's the order of filling and the order of that they exist in. So that's why they get listed the way that they get listed, at least in my head, because that's how they fill. Okay. Now, can you list them in a different order? Of course you could. Now, you'll see that they're like that in a lot of different places. The next thing we have to talk about is the energy of these orbitals. Energy increases as we go down the table. So S has a lower energy than, 1s has a lower energy than 2s. And of course, 2s has a lower energy than 2p. And you should be able to see that. 1s is below 2s, 2s is below 2p. We've drawn this such that we have a line for each orbital. And each distinct orbital has its own line. So if there are 3p orbitals, then we have 3 lines. Each line can have 2 electrons on it. Okay, so we can draw them on there, right? This shows us where those things exist. All right, so now I've got my 1s, my 2s, my 2p, my 3s, my 3p, and then something really interesting happens. If I continue up this energy thing, the next thing I hit is 4s. And notice we go 1s, 2s, 2p, 3s, 3p, and then we don't fill the 3d, we fill the 4p, or the 4s. So that matches. It's the next thing in the energy order, so it's the next thing that we fill. And then we go to 3d. Okay, it's the next energy that's here, so it's the next thing that fills. And so then we fill this guy right here. But I noticed that in this energy diagram, that's a 3D, which it is, it's 3D. And so my D block is an n-1. So even though this is 1, 2, 3, 4, my D here is a 3D. Okay, so it's always an n-1 when we talk about D. Okay, so my D's are always n-1. My F's, for reasons that are the same. I mean, really they are. That diagram is not here. It doesn't go that high. But for the exact same reasons, we have the F's that are down here, and they're an n-2. Now, I got shown this diagram, and then I got shown this thing right here, which is the order in which they fill. And they said, draw these and write these out in this order, and then draw these arrows, and that's the order they fill in, and just memorize this and be done. And I can't do that. I can't. I mean, I could. I can physically do it, but it makes no sense to me. I needed to make sense of it. It turns out that as we talk about these things, S's are really easy to fill. They're small. So if I put, one electron in it, that's good. 2 electrons is better. So when an orbital is half full, that gives us some energy stability. When it's completely full, that's a lot of stability. So an s orbital is really easy to fill because it's automatically half full or full, depending on how many things we put in it. When we get to the p's, right, we've got to have 6 total electrons to fill those. So it's a little harder to do, and that's why it's more energy involved. Okay, so we get some stability when we have 3 of them in there, and then more when there's 6. And so we do the S, and then we do the P, and then we do the S, and then we do the P, and of course, then the question becomes, well, go ahead and do that D block, because I've got a D block. But that D block either needs 5 for half full or 10 for completely full, and that is a lot of electrons. And it's more favorable to put it in the S block because I get some stability when I have that half full or completely full S block. Oh. So I get stability from filling that S before I fill that P or the D. Okay. So it's more stable filling the S before the D. That's why it happens that way. Okay. And that helps us to understand that. Now, the same thing is true when we get to the place where the F's exist. So when we have this F that finally comes in here, there are 7 electrons I need for half full and 14 for total. So it's way more preferable to go to that D first and do, things in a sort of different order than we would expect. Okay. And that is exactly what happens. Now, I try not to ask you about the energies down there. We could do it, but I try not to ask about the electron configurations for those. We'll talk a little bit about them, but there's that. Okay. So we see that there is a little bit of weirdness in the order in which we fill them. The other thing I'm going to tell you, and somebody finally pointed this out to me, it made a ton of sense. I know that this is an S block. I know that this is a P block. I know that this is a D block, which is n-1, and I know that this is an F block, which is n-2, right? And I can see that I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, everything makes sense up there. Then 11, then 12, then 13, 14, 15, 16, 17, 18, everything makes sense to there. And then I would have expected that we went into the D, but that next electron, that 19, goes into an S. My periodic table tells me that the next electron goes into an S orbital because that's where it is in the table. So I know when I'm doing my electron configuration that it needs to be in an S. So I'm reading that information from my table. Okay, so I know I need to fill that 4S before I fill my 3D. So 4S, 3D, 4P. So my table will tell me the order in which I fill these orbitals. Cool. So now I understand why they do what they do, but my table will also tell me the order in which they do it. So now I've got a key to tell me exactly what order they do it in. I understand why they're in the order that they're in. Cool. So now I don't have to memorize this either because I have a tool to tell me exactly what to do. Okay. Great. That's awesome. So now we've talked about all of this stuff, and you may have some idea what I'm doing with that. You may not. Why did I say all of those things? It's a good question. Yeah, let's talk about this. SPD, which is n-1, and my n is the row number. Sorry, n is the row number. So SPD D, and F, n-1 for D, and n-2 for F. Okay. And that's just the labeling. When I get onto a test, again, I immediately label my table with that because, I mean, I don't have to do it anymore, but I had to when I was a student because it helped me so much to see what I was talking, or to think through what it was that I was trying to explain. Right? So there's that part. Now, I want to talk about an electron configuration. First thing I'm going to say is you're responsible for writing an electron configuration. Okay, great. That's awesome. I need to tell you a few things about how we write an electron configuration. And all of this goes with writing an electron configuration. But what is an electron configuration? Well, let's talk about our friend carbon. So our friend carbon has 6 protons and therefore 6 electrons. So 6 electrons, they need to live somewhere. And I might want to be able to tell you where all 6 of those electrons live. So I might want to give you an address for all 6 of them. Oh, is that what we're talking about? Yeah, and there are reasons that I need to do that. Eventually, we need to be able to talk about the electron configuration so that we can talk about the ones that are on the outside, because those are the ones that are capable of doing chemistry. So we need to be able to write an electron configuration so we know who's on the outside and therefore how many electrons are available to do the chemistry. So now we're going to learn how to write a complete electron configuration so that we know where all of the electrons within a particular species live. That's what we're doing. Okay, we have a shorthand notation for how we do that. And we do that by writing the number of the orbital. So if I'm talking about this first orbital, I know that he's in the first row, so he's a 1. And you know that first orbital is an S type because he's in the first block, so he's an S type. You know that's the orbital that I'm talking about. And then depending on how many electrons we're talking about, this first row, if I talk about hydrogen, there's 1 electron that's present. So I signify that by putting him up here. So I have his row number is 1, his orbital type is S, and the number that are in it is 1. That's what I'm writing. Okay. Now, awesome. Now, a couple of things that we've briefly touched on that we need to talk about again. Electrons have spin, right? So they're either up or down. So when we draw these things, we sometimes draw them instead of writing them like this. So for this one, we would draw that as 1s, and we'd have 1 up, right? When I draw that next electron, it can't be like this. And that's what I was talking about before. It's going to have to be 1 down. Convention says that we draw the up one first. It's really just so that we always do it the same way. It's not necessary to do it that way, but that's just how we do it. It again, is a convention. We show this by drawing the arrows for each electron, either up or down, depending on their spin. Okay. The Pauli exclusion principle states that in one orbital, you can only have 1 electron with 1 up spin and 1 with a down spin. Okay, so again, they have to pair in a hetero fashion, 1 up, 1 down. Now, this guy Hund, his rule says that I'm not going to pair if I don't have to. Well, I can't talk about that when we're talking about putting 2 electrons in an S, because they can only go in that one place, right? But let's talk about P for a second. The first place I have P is 2. So if I'm in 2P, there are 3 of them. So there are 3 P-type orbitals. There's my X, my Y, and my Z. And if I want to put electrons in them, then I can do that. So I put my first one in, and he goes here. Because why not? When I put my second one in, what I'm hearing from Hund is that I'm not going to put him in like that. Why? Because I don't want to share if I don't have to. If there are multiple rooms available in my apartment, why would I put two bodies in one room when I could have one body in each? There are energy benefits to having both of these things be half full comparative to one of them being completely full. Okay, so we are going to do it that way. We won't pair unless we have to. So until I get 3 of them in there, well, technically till I have 4, then pair. We always draw it in the first one. That's just, again, a convention. But I don't pair unless I have to. Okay. So in the P, I don't do it until 4. In the D, I don't do it until 6. In the F, I don't do it until 8. Okay. Cool with that. So don't share unless I have to. Always have to be 1 up, 1 down. And I write my addresses with the number and the type and then how many. Okay, so we wrote 1s1, and that's hydrogen, because hydrogen only has 1 electron. So the address for that 1 electron is this 1s1, which is what I wrote right here. 1 electron present in 1s orbital. So that is the electron configuration for the hydrogen atom. Oh my God, I wrote an electron configuration. Yes, I did something. That's awesome. Okay, I did 1. Let's talk about some more. Now, I say electron configurations for atoms are easy. I think they are. And I tell you to follow the table. Okay, we did hydrogen, right? And we said that he was a 1, he was an S, and he had 1 electron in that orbital. The next thing that we would do is helium. Helium is in that first row, so we're just still talking about 1. It's still an S-type orbital, so it's still 1s. How many electrons are in it? Well, there's 2 electrons I need to account for, both of which can go in that S-type orbital. So instead of having 1 here, we'll have a 2. That's helium. Ooh, okay, let's talk about lithium. Lithium is in the second row. Now, I always build on what I had before. So when I get to that second row, I always have to have a 1s2 first. So it's always going to be 1s2. It's always the noble gas core from the row before. Ooh, interesting. And we'll talk about that again in just a second. So that 1s2 is still there. Then I have to look and see what's past that. So when I come to lithium, he's in row 2. So I know it's going to be a 2. What type of orbital is this electron in? Well, it's still an S-type, right? Because remember, it's an S-type, so it's in the S block. So that's an S-type orbital. And how many are in it? It's just 1 additional electron that we've put in it. So it's a 2s1. So is there an alternative way that I could write this? Yes, there is. Because I know that I have that noble gas configuration from the one before it, I could write this as the noble gas before it, which is He, and then whatever's beyond that. So the next thing is 2s1. What you're looking at here is a full electron configuration and a noble gas config. Now, here's when I tell you this. Chemists are lazy. Okay? There are reasons that we do this. So those noble gases are called noble gases because they don't do a lot of chemistry. Can they? Yes, they can. But they don't do a lot of chemistry because they're extremely stable. Extremely stable. they're completely full in their S and their P. So they've got as many electrons as they really want. They don't want to give any up. They don't want to get any more. And so that means that this set of noble gases is where everybody wants to be. Right? Everybody wants to be a noble gas. And so we don't see a lot of chemistry that happens. So if I write that noble gas configuration, not only do I always have it, but it's unlikely to do any chemistry and therefore is not interesting when I'm talking about what's available to do chemistry. So it gives us a lazy way to do it, but it also tells me that that's not going to be the part that's interesting in terms of the chemistry. Okay? So there's that. All right. So we now have our lithium. The next guy on the table is beryllium, E. Okay. And our Be, we add one more electron to it. That means I still have that one S2. I'm still in that S block, so I've added to another one to the S. I'm still in row 2. It's still an S block. And now I have 2 electrons that are in there. Cool. Okay, who's next? Well, turn off my P block. The next one I go to, so this is 4. The next one that's available is 5. So he's right here. All right, okay. He's 5. I have that 1s2. And this is for boron. I have the 2s2 from the beryllium. So whatever I came before me is still there. 2s2. And now I'm still in row 2, so it's a 2. The number in front of it is still 2. It's a p-type orbital. And there's 1 electron that I need to put in it because I only added 1 more, right? So 1s2, 2s2, 2p1. And strangely enough, what you'll see in the middle there, so, and I can't come off of this and show you the middle, but in the middle there, where it says boron, and then it says supply risk, it says key isotopes, 11b, electron configuration. And I just wrote exactly what it says. Okay. So I can come here and check my electron configurations. There are lots of places that you can do that. Some calculators actually have them in it. So some people have that available. I unfortunately cannot do anything about that. It's a thing. Okay. So that's something we have. So this is an HE with a 2s. 2. This is an HE with a 2s. 2. 2p1. Okay. Well, that is very cool. Very, very cool. I'm going to take a break at this point. I'm going to cut this into 2 videos. And then I'm going to go ahead and come back to it. What we're going to talk about is how we do the next field, right? I want you to think. I want you to stop at this point and think to yourself, how would I do the rest of them in this row? So how would I do carbon, nitrogen, oxygen, fluorine, and neon? Okay. What would both of these configurations, the full configuration and the noble gas configuration, look like for carbon, nitrogen, oxygen, fluorine, and neon? And like I said, I will be back. Stop sharing video, and I'll be back.